So the battle plan today is to finish up on the work we were doing at the end of Friday on data representation. And then we'll try to do that pretty quickly. And then we'll actually start it up on Jest. We'll actually pull Jest up and walk through some of its main features and get you started on that so that hopefully things in chapter 2 will make sense. First, are there any questions about anything so far? Are there people having trouble getting Jest to work on your computer? Issues with Canvas or Slack? What? Your address doesn't work? Oh, Jest doesn't work. In what way does Jest not work? Like you double click on it and nothing happens? Or so that's probably a Java problem. And those are hard to debug talking. Like I think we probably need to have a Zoom meeting to try to fix that. So if your Jest isn't working, it's probably something like normally I just have you come to office hours and sit in my office and we do it together, but that involves sitting next to each other and breathing nasty terms on each other, and that's not good. So having a Zoom meeting where you can share your screen and I can sort of see exactly what's happening is probably your best bet. So I would, there's a bunch of sign-up slots for tomorrow. I would maybe grab one of those. And usually it's been pretty fast. And I've helped a couple of people that were having trouble, and we've usually been able to get things resolved in a matter of 5 or 10 minutes. There's been at least one instance that took a while, but usually it's been pretty quick. So that's probably what I would do. Does that make sense? Anybody else having issues? Okay, so you double click. It seems like everything was installed, but you double click on it and nothing happens. So the problem, when that happens, it's usually, and that's a Windows box, and that's a Windows box, right? With a Windows box, the problem is almost certainly a problem with your Java installation, actually, not your Jest. And so going back in the write-up and rechecking the Java pieces and making sure they're saying the right thing would be the first thing I would try. And that's, if we Zoom, that's what I would do as well, is I would have you do some of those commands so I can see what the actual result is. So you can have a look at that, but it's all kind of cryptic and mysterious. So if you're looking at it, it's like, this doesn't make any sense, then I would definitely recommend setting up a meeting if that works. Is that a plan? Anybody else having issues or anybody got questions? Going. On. Okay, coolio. So I'm going to move the laptop and connect the tablet again. I'm actually going to try this over here. I've got more room. Tablet. One here, tablet. Too many cords. Okay. Plug in the tablet. Share whiteboard. Okay. So, folks at home seeing the whiteboard, empty whiteboard? Cool. Okay, and this works, yes. Now, for those of you in the room, one weird thing is I can see the computer, but I can't actually see the screen because now I'm looking. It's kind of cool because I'm actually looking at you as opposed to writing on the whiteboard where you all see my back, which is kind of like, so this is sort of nice in that regard. But if there's a problem on the projection, I would have no idea. So definitely let me know if there's something weird happening behind me, you know, so that I don't just embarrass myself by continuing to babble on while you think he's lost his mind. That would be bad. Okay, so we had left Friday with determining, we figured out that if we have wow, my handwriting's terrible on this thing. N bits, we can make we can make 2 to the n patterns. So we don't really need a lot of bits to be able to make a lot of different things. So in particular, it's worth knowing that 2 to the 10 is 1024. So with 10 bits, we're actually on the order of a small adult vocabulary of words. Like, you know, human usage is actually, like, regular usage is probably a few hundred words. Most adults know maybe a few thousand words, many of which they don't use very often. So with 10 bits, we're sort of in the neighborhood of a vocabulary for an adult. 2 to the 20 is about 1 million. Patterns, okay? So we could make 1 million different patterns with 20 bits, a little more than that. And 2 to the 30 is approximately, two to the 30 is approximately 1 billion. So with 30 bits, we can make something over 1 billion patterns, which is a lot, okay? So we can make a lot of different patterns with not that many bits. And in some sense, this is old news, right? The English alphabet only has 26 letters, but we can clearly say a lot more than 26 things by combining letters into larger groups, right? By allowing ourselves to form words out of anywhere from 1 to, you know, a lot of letters, but, you know, for most words, probably not more than like 6 or 7. We can make a lot of words with not an infinite number of letters. This is the same thing, essentially. We're using a small number of bits to make collections of bits to make really large numbers of patterns of possible bits. In the same way that we can use a handful of letters to make a lot of words. Dictionary is full of words. Okay. Does that make sense? Questions? Okay, so the other thing here is we want to be, oops, I'm going to make it a new screen. Are there questions about anything before I move away from the screen? Okay. We can, question is, okay, great. We've got this idea that a group of bits can represent something. But how do we represent things we care about? Okay, how is it that we turn patterns of bits into data that matters to us? And there's a whole bunch of different kinds of data that matter to us, right? So we care about representing numbers, we care about representing strings, we care about representing, in this class, pictures and sound, right? You watch videos online all the time. Maybe use spreadsheets, right? There's a bunch of different data that we want to be able to represent. And so there's a question of how do we do that? And that's one of the things that we'll learn over the course of the class, how different kinds of media data are represented, okay? First thing we're going to do, though, is talk a little bit about numbers. Now, I'm curious. Oh, come here. Save yourself. So, how many people, and just raise your hands, how many people are familiar with like binary numbers? Is that a thing that you've ever heard of? Anybody? A handful of people, but not everybody. That's totally fine. I was just curious. So let's actually quick review that. And the basic idea with binary numbers is pretty similar, actually, to the things that you're already used to. So you know, for example, that if we have the number 5, oops, that's not very 5, 8, 2, 7. Let's say 5,280 or 5,827. Now, we know how to read this in positional form. We know that the position of the digit tells us how big that part of the number is. That the 5 is a bigger deal than the 7. And we know that because of the position in the number. Does that make sense? Right? And so, in particular, we know that 7, we interpret that as 7 times 1, which is actually equal to 7 times 10 to the 0th power. Now, you may or may not remember from some version of high school algebra, but if you raise something to the 0th power, it turns out it's 1 for anything other than 0. So 2 to the 0 is 1, 7 to the 0 is 1, 10 to the 0 is 1, minus 2 to the 0 is 1, 0 to the 0 is undefined and blows up the world, so we don't think about that. Okay? But all the other things, if you raise them to the 0th power, you get 1. And this 2 here, that's 2 whats? It's not 2, it's 2 times 10, right? It's 2 tens. So we had 7 ones in the first position. We had 2 tens in the second position. So that's 2 times 10 to the 1. Okay? Does that make sense? And now 8 is what? 8 whats? 8 frogs, 8 geese, 8. Yeah, it's not ones, it's not tens. Now we're at hundreds, right? So it's 800. And 100 is 10 squared. Okay, with me? And then the last guy over here, so this was 5,827. So we have 800s, we have 5,000s. And is the writing big enough in the room, in the back? Are we doing okay? Just wanted to check. And are we doing okay online? Is everything readable? Good, thank you. Okay, so we have positional notation. We know that on the right, we have the ones, then the tens, then the hundreds, then the thousands, right? This should ring some bell from like the 4th grade. It may not have been done with powers of 10 like this, but the idea that you had ones, tens, hundreds, thousands, 10,000s, etc. That stuff you learned as a kid. You may actually have forgotten having explicitly learned it. It might just be stuff that's in your head. And you don't have any memory of having actually covered that. But it would have been one of the things that you would have covered in math class, probably in elementary school. And the pattern, and this is very important, is that each position is a higher power of 10. So that as we keep going, we would have, the next position would be 10,000, and then 100,000, and then we'd have millions, tens of millions, hundreds of millions, billions, right? So we'd have increasing powers of 10 as we add positions to the number, okay? And binary is the same thing. It's just powers of 2 instead of powers of 10. Okay, so it's something you've done and that you're actually quite familiar with. You're just not used to doing it with powers of 2. So so this is what's called decimal. Decimal. So powers of 10. And that's the notation we're used to. And we're used to it mostly because we happen to have 10 of these, right? We have 10 fingers. And we count on our fingers. And so that's probably, I mean, nobody knows for 100% sure, but the fact that decimal is super common and we have 10 fingers is probably not an accident. We probably do decimal just by the accident of having 10 fingers. If we had 8 fingers, we'd probably use octal, which is the fancy name for base 8. If we had 12 fingers, we do, I think it's duodecimal, is the fancy word for base 12. I don't actually know. If we had 16 fingers, we'd use hexadecimal, which is the fancy word for base 16. So it's a, it's a historical accident that we have the fingers that we have, and that we use base 10. Computers, in some sense, happen to just have switches. So they do everything with base 2, okay? And so in binary, which is base 2, I guess I should say base 10 here. In binary, we do the same thing, but we use powers of 2 instead of powers of 10. So if I have like 1, 0, 1, 1, this is going to be 1 times 2 to the 0. Erase. 2 to the 0 equals 1 times 1 equals 1. So that's going to be a 1. This is going to be a 1 times 2 to the 1, because our positioning, right, we have 0, 1, 2, 3 for our positions. So we're at the 2 to the 1 position, which is 1 times 2, which is 2. Okay? Are we with me? Questions? Then this is 0 times 2 to the 2, which is 0 times 4, which is 0. Okay? And then this guy here, actually, because I'm getting close to the bottom of the board, I'm actually going to put him on the top. This is 1 times 2 to the 3rd, which is 1 times 2 to the 3rd is 8. So this is 8. Okay? With me? Questions? So then this adds up to, if we add all these together, get this right. So if we add all these together, we get 8 plus 1 plus 2 is 11. So 1, 0, 1, 1 base 2 is 11 base 10. 11 in the way we think about numbers more normally. So this is how the computer is going to represent the number 11. It's going to represent it as 1, 0, 1, 1. that make sense? Questions about that? Do you feel like if I gave you a pattern like this, you could generate the decimal equivalent? People nodding cautiously, somewhat nervously. Seemed to make sense when you did it. Can I do it when I get home? I understand that. So we'll have a chance to try this, and it'll be in a quiz that you can take more than once. So if you get into it and you're like, oh yeah, I don't get it anymore, then we can certainly talk. Questions about this? And, you know, I just did 4 bits here. We could do many more bits, and we would just have larger powers of 2. Right? It's just the math becomes more complicated. Like you might have remembered or been able to figure out pretty quickly that 2 to the 3rd was 8. But, you know, you probably don't have any idea what 2 to the 8th is, or 2 to the 16th, right? Unless you've hung out with computer science people for way too long. These are not things that you would have memorized. And that's fine. Like, you don't need to have memorized them. And you don't need to memorize them for this class. So we'll stick to small numbers here. And, you know, frankly, one of the things is if we need big numbers, you ought to use a computer anyway, because the computer is good at this. And this is kind of tedious and boring for people. But we need to understand the basic setup. So, questions about the numbers thing? Any questions online? Doing okay? Online peeps? Okay. So this is how we can represent, and actually I've lied a little bit here. I said numbers like this was all numbers. Actually, all we figured out how to do here is represent what are called natural numbers. So whole numbers 0, 1, 2, 3, 4, 5, and up. We haven't talked about negative numbers. We haven't talked about fractional numbers, so 2/3 or 10.5, right? We haven't talked about complex numbers, if you've ever dealt with those, right? So there's a whole bunch of kinds of numbers we haven't dealt with here, but this is enough to be getting us going. And in fact, it turns out this kind of number, these natural numbers, are all we need to handle all the media representation that we're going to use in the class. We won't actually need to care about fractions and things like that. It'll all be whole numbers like this. There are ways to represent those other kinds of numbers. I just don't want to get us bogged down into like a fully detailed description of all of the different ways that we can represent numbers. Okay? Questions? Awesome. So this gives us how do we represent numbers with bits. One thing we don't have yet, and I'm going to actually go to a new blank screen. So if there are questions about this screen, holler. Going, gone. So we can represent numbers. As sequences of bits. How do we represent characters? Represent characters or text. And if you think about it, actually, you know, you probably don't do a lot of number stuff with computers. You use computers all the time, but you probably don't use them to do math very often, unless maybe you're a math or a stats major, or doing accounting or something. You probably are far more likely to use a computer to manipulate text. You write, for example, emails and text messages all the time. And those are text. They're not numbers, okay? Your text messages to your friends are probably not calculations that you do math on, unless you have a very interesting group of friends. You write papers for class. That's text. You read things on the internet, okay? Twitter, Facebook, stuff like that. That's text, okay? So a lot of what you do with the computer is actually text, and very little of it's actually numbers, okay? And the other big thing you do is probably media, right? You look at pictures, you look at films, movies, TV shows, videos, you listen to sounds, you listen to music. So that's actually the stuff you tend to use your computer for a lot, not doing math, okay? So that initial idea that computers were sort of big calculators was true for a long time, but has turned out really in the last probably 30 years to have become much less true. And computers are used much more to do other things, process text, process media, okay? That's a much more common use. So how do we actually represent text? Well, this is actually a place where the decisions are kind of arbitrary. Basically, we're going to assign a number to every letter. Okay? So we're going to just assign numbers to letters. And the assignment could be really quite arbitrary. It doesn't really matter how we assign the letters to the numbers, as long as every letter gets a unique number, right? It's important that we be able to tell the difference between E and A, so E and A better get different numbers. But other than that, like E could be 7 and A could be 112, or E could be 8005 and A could be 2. It really doesn't matter a lot. As long as we agree, it's crucial that we agree on what numbers we're assigning to the different letters. Because if I have a table that says A is 42, and your table says 42 is X, and I send you a message as a sequence of numbers, okay? Because that's what's going to happen. We're going to turn the letters into numbers, and the numbers get turned into zeros and ones, and that's what gets sent over the internet. You get the zeros and ones, you convert them back to numbers, you say, oh, this letter's 42, you look at 42 in your table, and you get an X. When I thought I was sending you an A, you can imagine chaos ensues, right? It is clearly very bad if we don't agree on what the representation is. So the representation is arbitrary, but it's crucial that it be what's called standard. So we have to have standards. So we have to have standards, or it's real bad. And so in computing, there are often bodies, organizations, whose job it is to manage standards. Make sure that everybody's on the same page, so that if you download a web page from some other place, it'll work on your computer, and that they didn't make a different set of assumptions than your computer did. Because if they did, it would be chaotic and crazy. And there have been historically fairly big fights over standards. IBM had one standard for assigning numbers to letters called ASCII. Bizarre name, only a computer scientist could love. And everybody else used a different standard called the ASCII table. And for years, there was this big fight where IBM was like, no, 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 you should all use ours. And everybody else was like, no, you don't want to. We want to use ours. And it meant that if you had a document on an IBM computer, and this is not like an IBM laptop, we're talking IBM sort of big computers that take up buildings back we're talking in the 60s, that if you had an IBM computer and you had a document on it, and it got transferred to somebody that was using, say, a DEC computer or a UNIVAC or some other company's computer, it would have to be translated from the IBM standard to the ASCII standard before it would make any sense. So you had to have these things that would do this translation when documents moved back and forth. It was a real nuisance. In the end, EBCDIC lost, and everybody kind of said, too bad, and IBM gave that up. And people went with the ASCII standard, okay? And ASCII here is, so the ASCII, ASCII standard was used for decades. The problem with ASCII was designed in a universe that assumed that the only people that used computers were basically Americans and spoke English. It was really super American English centric. It was designed by people in the United States in the US computing industry, and it really didn't acknowledge that anyone else existed in the universe. So it basically did A to Z, uppercase and lowercase, the letters, the digits, and the standard US punctuation marks, and nothing else. So there weren't even ways to represent things that were fairly common in the Latin alphabet in other languages. So an N with a tilde over it in Spanish, C with a funny little tail under it in French. These were things that you couldn't do in the ASCII table. That's not to mention, what do you do about Korean and Hebrew and Arabic and Chinese and Japanese and Thai and Navajo and, just a bazillion other languages that don't use the Latin alphabet, right? There was no way to represent those languages. Those people were really out of luck. And so there was all this weird stuff that happened, and we won't get into it, but it was complicated at best. They often had sort of country-specific representations, but then documents from one country, if they moved to another country, you had problems sort of translating. It was a real pain. And this became really problematic when the web developed in the 90s. Before the World Wide Web, documents didn't move around the world all that much. They might move within a company. Say a company's got an office in France and an office in Tokyo, right? They might move documents around internally, but those might all be in English, for example. A company might just say, well, to keep the world simpler, we'll just make one language our standard, and all our documents will be in French, right? And then we don't have to worry about this translation business. Well, then you get the web, and now all of a sudden I can look at websites in Korea. I can look at websites in Nigeria. I can look at websites in Jordan. Well, how is that going to work, right? Everything's messed up. And so a standards body came into the world to manage that problem. And a new standard was created called Unicode. Unicode. And Unicode is the common standard now. And because ASCII was so prevalent for so long, Unicode basically is a superset of ASCII. So it uses the ASCII assignments for regular English, American English letters, but then it allows for assignments for all these other character sets as well. So in Unicode, you can have Thai, and you can have Korean, and you can have Arabic, and you can have Hebrew, right? You can have all these different things. There's, in fact, actually a full Unicode support for Klingon, because nerds are nerds. And so somebody was like, well, we got to do Klingon, I guess. There's also emojis actually live inside of Unicode. And there actually is a committee that decides on the creation of new emoji standards. So you think there ought to be an emoji for a particular thing, like, oh, because of coronavirus, we ought to have all the standard emojis, but with masks. You would go to that body and you would say, here's my proposal, and a group of smart people would sit around and debate whether that was a good thing to add to the standard. And if they agreed that it was, then that would get added. And then graphic artists would busily go out and make all these masked versions of face emojis, okay? The decision to have emojis with different skin colors, if you want to think of it that way, like a committee had a meeting about that. The fact that there's a poop emoji, like smart people had a meeting over the poop emoji. So, you know, life is weird, and there you go. But there is a body that actually manages that stuff, okay? And if you feel like there ought to be a new emoji for something, there is a way to do that. There is a process, and you can go and make a proposal. And if you can convince them, then lo and behold, your emoji gets added to the set. Okay, so questions about any of that? Now, if you want to see the ASCII table, here I'm going to actually, is it okay if I quit sharing the screen with all these words on? Questions? Stop sharing. And when the video gets posted, it'll have all these screens. And I can also share these screens separately just as images. Canvas saves them as JPEG files, and I can post those as well. So if you ever want to see the slides or the whiteboard from class, that'll get posted. Okay, so stop sharing. If we share this, if you if you search for ASCII table, you'll find that there's ASCII-table.com, there's ASCII-code.com, and et cetera, and et cetera. And there's actually a Wikipedia entry on ASCII. And if you go to any of these, you can find the table. And I think if we scroll down, there's actually a big table version of it. And a lot more history than you care about. So, okay, so here's where it gets interesting. So, for example, the space character, and this is really important. People often don't think about the fact that the space character is an actual character. In a text, you would actually have to have a character there. Like, it's not the absence of a character. It is an actual character that says, I am a space, right? And so if you have the text, hello world, okay, that's going to be 5 letters for hello, and 5 letters for world, and 1 for the space that's in between them. So that's a total of 11 letters to say hello world, not 10 letters to say hello world. Does that make sense? Okay. And so the space character is decimal 32 and binary 0100000. Okay? And it turns out that this is in the 5th position, or well, it's the position 5 counting from 0. So 0, 1, 2, 3, 4, 5. And so 2 to the 5th is 32. And that's why this turns out to be 32. It's also 040 in base 8 and 20 in base 16. You don't care about those. But that's what those columns are telling you. Oct is base 8 and hex is base 16. Decimal is base 10, sort of normal numbers, and binary is base 2, what we just talked about. And so a space is 32 in ASCII. So that was a decision some people made back in the 1950s, and that's what we still do. Because again, it's kind of arbitrary, and as long as we agree, we're good. An ampersand is 38. The digit 0 is 48. The digit 7 is 55. Capital J is 74. At symbol is 96. Little g is 103. And notice that upper and lowercase are different. Like a little a is 97. We scroll back, a big A is 65. So we have to have different representations for uppercase and lowercase letters. They're not the same thing. So if I want to represent hello with a capital H, then that first letter is going to be 72. If I have the word hello with a little h, then that first letter is going to be 104. So that kind of thing matters. Okay. Does that make sense? Questions about that? And again, you don't need to memorize this. This is not something that would be a good use of your brain cells. Knowing that it exists and knowing how to look things up in it, very important. Actually knowing the numbers, not super important. Like I can tell you a handful of them, like the fact that 32 is space comes up a lot, so I happen to know that. But I couldn't have told you what A was without looking it up. No idea. And I certainly don't know any of the digits or the punctuation marks. Okay? Because I don't need to know them. You know, the table knows them, the computer knows them, and that's what really matters. So you don't need to memorize this. Don't forget about that. Knowing it exists, knowing why it matters is important. Memorizing it is not. Question?
Some characters might have the same code as two different characters.
Yeah, so you're thinking like these guys right here?
Yeah.
So the question, I think at home you probably couldn't hear that. The question was, there appear to be some characters that have the same code and what's going on there. So here, the code for 92 seems to have several options. 94 and 95 also have several options. These are historical weirdness, is the short answer. So as an example, the 94 and 95 were left arrow and up arrow. And they map, the alternatives for those is caret, the sort of pointy hat thing, and underscore. And early keyboards often had a different set of characters. We also had to standardize on characters in the same way, especially on the oddball punctuation characters. And on a typewriter, if you think about a typewriter, you would never need up arrow and down arrow. You can't really use arrow keys to move around on a physical typewriter where there's a roller and all that sort of stuff. Like, that's just not how typewriters work. When we went to computer screens where you could use arrows to move back and forth and up and down on a screen, then all of a sudden an arrow became a really useful thing. Like keyboards often didn't have arrows. So people would say, well, nobody uses the caret key very much. We'll put an arrow there instead. Or nobody uses, this other punctuation mark very much. Like a lot of our early typewriters actually had, as well as a $sign, often in the US also had a cent sign, like the C with the line through it, which you don't see very often. But old typewriters often will have that. And they're like, yeah, who needs that? We'll put some other thing there that we need. And so these are situations where that same code, depending on what computer you were using, might have meant different things. So this is an example where there's a standard, but the standard's not fully standard. Like, we haven't agreed on everything, we just agreed on most of it. So I might be like, hey, I'm ASCII, but I'm using the arrow keys. And you're like, oh, I'm ASCII, but I'm not using the arrow keys. I'm using caret and underscore. And then we have to be a little careful, because if you send me a document with 95 in it as an underscore, my computer might display it as an up arrow, which would be problematic, right? So there were some wrestling matches there. In Unicode, all that's been resolved. There are separate things for up arrow and underscore, but here, not entirely. So that was a great question. Thank you. Does that make sense? Other questions? And I think with the mass and everything, it really makes it harder to ask questions, and I just keep talking. It's harder for me to read people's faces. Like, are you thinking of asking a question? And so please, be bold and, do the good thing and ask the question, because that'll make the class way more interesting for everybody else. If it's not just me babbling. Other questions about this? One of the things that you'd asked about the multiple characters, if we go back to this first, so from 0.0 down to decimal 31, there's a whole bunch of weird things here, like negative acknowledgement. What the hell is that? Shift in, shift out, carriage return, form feed. So a lot of this stuff was actually, these were control characters for literally controlling typewriters. So early computers often had a physical printer instead of a screen. Like, we're talking very early 50s into the 60s. So instead of screens like we're used to, you might have a keyboard and literally a roller and paper that was coming out and had the letters on it when the computer generated a message. Instead of it being on the screen, it would. And things like backspace, horizontal tab, line feed, vertical tab, forward feed, carriage return, these are all about controlling that device, like rolling the paper forward, rolling the paper backward, moving the head of the printer thing left or right, that kind of stuff. So there's some weird historical artifacts in here that we would never use anymore, but are there. And number 7 decimal is bell. So those early teletypes literally had a physical metal bell attached to them, and it was a way of getting the operator's attention, because often there was a lot of stuff being printed, and there was a person whose job it was to sit in a room and keep an eye on the machine. And because there's so much stuff coming out, the person's not going to go over and look at the printer every time it says something, especially since these were slow, per letter. Like, you could hear every letter being printed. And the bell was a way of saying, the message is done, come over and look at it now. Or bing, bing, bing was like, something very important has happened, you should look at it right this minute. And so there literally was a bell character whose job it was to ring that physical bell. And on most computers now, if you try to print the code, the character 7, it'll make the computer beep. And that's sort of the modern version of the old bell. So weird stuff like that is still sort of floating around in the universe. None of which is important to you or matters, but I like telling stories. So there you go. Okay, questions about any of that stuff? Let's pull up Jess and actually poke at Jess a little bit. Okay, so I'm going to need to grab another. Oh, actually, I don't know if I need to grab another computer. We're going to find out. I'm not convinced they've installed Jess on this yet. Oh, hey! Oh, well, it's just 5, but maybe that'll be enough for today. If it actually works, we'll. Oh, maybe this will be a thing. Okay, awesome. You're gonna work. You're gonna work. You're gonna work. Come on, work. Da-da-da-da. And I'm gonna actually disconnect. Oh, hey, it looks like it worked. So this is a slightly older version of Jess, and I'll need to talk to them about installing the more up-to-date version. But this is at least, this will get us where we need to be today, so that'll be fine. Okay, so I'm going to disconnect this, and I'm going to come back over here so that I can see everybody a little better. I can see the whole room. So this is the Jess environment, and we're seeing this okay at home? People online? Good? Okay. So here's Jess. Now, the Jess screen has two main components. On the top is what's called the program area, and on the bottom is called the command area. And we can move this dividing thing to change the relative size of these, and you can obviously change the size of the whole window on your computer, blah, blah, blah. And when we get to the point of writing our own programs, they're going to go in the top area. That's where we'll write programs in the program area. The control area or command area at the bottom, that's basically a fancy calculator where we can run things, we can type commands and compute stuff. And we can type and compute all kinds of things here without having had written any programs. So we could say things like print 2 plus 3. Woohoo! We got 5. Okay. Now, is this readable in the back and in the room? The contrast and the color scheme's a little weird, perhaps, for the projector. If you're having trouble reading that, I can change the colors. At the moment, I'm keeping it this way because it's the same as what you would see. But if you would like a different color combination, like black on white in the bottom as well, we can certainly do that. Because white on black doesn't project super well. It looks good on a screen, but it doesn't project very well because the contrast is hard. Questions or issues on that front? Okay, so notice, I can say print, and I can print values. I can also print strings as values, and I need double quotes, not single quotes, around a string. I can print strings, okay? Is this visible okay at home for the online folks? Is the sharing working? You can see okay? Okay, thank you. Now, as the first line says, we can do basic math. So we can print, if we need to, do some calculation, we can compute 3 times 8 minus 4, and we find out that that's 12. Very exciting. Okay? Not really very exciting, but I'm pretending. Okay? Print is a built-in command in the language Python. So we've actually learned a command in Python, which is if we print a value, it prints the value. Okay? And so in our programs, if we print values, those values will appear on the screen when we run our program. Okay? And there are various built-in math functions. So we can say print ABS, that stands for absolute value. And the absolute value of a number, if it's positive, it's the same thing. So if we say absolute value of 7, we get 7. But if it's a negative number, we get the positive version of it. So the absolute value basically strips off a minus sign if there is one. And otherwise, it leaves the number alone. And I think we can print like the sign of things. Yep. So sign and COS, SIN for sign, COS for cosine. These are built in, TAN for tan. These are built-in commands if you need to do trig for some reason. Okay. Python supports that. Life is good. Okay. Questions about any of that? You don't need to memorize all of these. It's just the idea that there are functions and that we can call them and get values back. Okay. Now, and this connects us to the ASCII code stuff. Jess also knows how to do character encoding. So we can say there's a function CHR that takes a number and gives us the letter associated with that number. So 65 is the ASCII code for the capital A. And so when we said CHR 65, we got a capital A back. Okay? And if we do print CHR 66, we get capital B. Turns out that the letters are all adjacent. The little letters are adjacent in one section of the table, and the capital letters are adjacent in different sections of the table. Okay? So we can use JES to figure out what the values are for different letters. So if we wanted to figure out what my the ASCII for my name are, my name is, oh, actually, let me go the other way. So there's also a way we can go from letters to numbers. There's a function called ORD, O-R-D, which stands for ordinal, which is not helpful as a name, but there we are. ORD takes a letter and tells us what the ASCII code, actually the Unicode code for that letter is. And so capital N is 78, and little I is 105, and little c is 99. So the ASCII Unicode for my name is 78, 105, 99. And then if we turn that into binary, you get a sequence of 8 strings of binary characters, one representing 78, one representing 105, and one representing 99. And I could then send that to you. You could convert that binary back to numbers, look those numbers up in the ASCII table or using Python, and you would say, oh, that was Nick, as opposed to and, or the, or any of a number of other 3-letter words. Okay. Does that make sense? Questions? So ORD and char allow us to move back and forth between the numeric representation and the ASCII representation. One thing that doesn't work that you might think might work is that maybe if I did print ORD of the string Nick, it would give me those 3 numbers without me having to do 3 different calls. Yeah, not so much. I get a great icky error message. So it says the error value is ORD expected a character, but a string of length 3 was found. So instead of giving ORD a string with 1 character in it, you gave it a string with 3 characters in it, and it was like, yeah, I don't know what to do with that. And so it just died. And so you can't do that. You have to actually convert them one at a time. There actually is a trick that would allow us to process a whole string, but I'm not going to talk about that today because that would really confuse the hell out of you. It's confusing enough as it is. So we will skip the trick for now. Okay, questions about where we are at the moment? Now, the one other thing, given the time, let's do a little of the file stuff that's in the book. So there are, so all the functions we've seen so far are kind of standard Python functions. They would be part of any Python system that you would use. There are also functions that are specific to JES and this class. So the people that wrote the book and wrote the software created a whole group of special functions to help you manipulate media images. And those functions are not part of normal Python. They're specific to JES and the work we're doing here, okay? So most of what you're going to be learning will work anywhere in Python, but there are going to be specific things that are JES and not regular Python. I will try to identify the differences when I think of it, but I may not always remember, and so feel free to ask at any point, like, hey, is that a Python thing or is that a JES thing, okay, if you're not certain. So one of the things that they provide is a function called pick a file. this illustrates, here, let me, I'm not sure how to get the bottom up a little higher, because I think the bottom of the screen's a little low in the back. I apologize. Normally I would know how to do this, but in Zoom, it's a little less clear. So I think Zoom's going to just try to, what if I resize this, what happens? Well, I don't know if that really helped. Like that. Is that a little better in the back? Okay. So pick a file illustrates a common capitalization with functions in JES, which is functions where their names are sort of multi-word names, are lowercase first word, uppercase all later words. This is called camel case because the case goes up and down and up and down and up and down, like the humps on a camel. Somebody talking about that. But they use camel case for the naming of their functions. So pick a file, we have a little p, and then a big A and a big F, okay? And pick a file, when we run pick a file, it brings up a file chooser that allows us to go pick a file. And we can pick whatever file makes us happy. Probably nothing in here, right? Oh, there is. Well, no, probably not. Yeah, I didn't think so. Let's see, where can we? Well, there's probably something in downloads. Yeah, there is. So I'm going to pick this. And what it returns is what's called the path to that file, which is, you're not used to seeing paths probably on computers because you're used to dealing with files and folders as GUI things where you click on a folder and it opens it up and the files are all in a window. But internally, every file has a full path that describes where that file is in the file system. And what this is saying is that there's a folder called users, and in that is a folder called McPhee, and in that is a folder called downloads, and in that is a file called Java Setup 8u261.exe. So this is describing the file in a folder, in a folder, in a folder, in a text form, instead of in the sort of graphical form that you're used to seeing. Okay? And on a Windows box, you get the C colon at the front to indicate that this is all on the C drive. On a Mac, you'll get something similar, but you won't get the C colon, and you won't get, the slashes will go the other way. Pretty much everybody uses forward slashes to separate directories, except for Windows that use backslash. But Windows is like the only thing that uses backslash. So anybody who's not on a Windows box is going to see a forward slash there. But that's, a technical detail, not something that we care a lot about. Okay, we'll talk more on Wednesday about doing something with the file, but this should get us going. If you've got just going, you should definitely be reading chapter 2 and trying the examples in chapter 2 and making sure they work and make sure you understand them and ask questions if you got any questions. Okay? Anything else? Anything online? Peeps? Okay. Rock. See everybody later. Stay safe. Wear your mask, wash your hands. Yada yada.